If you look at page 79 of the separate worksheet that I sent to you last week, this one is question 5 on the page 79. Now here, you have a variation with potential difference V of the charge Q on one of the plates of a capacitor. This is a straight line graph that passes through origin. Okay, so here they mentioned that the capacitor is connected to an 8-volt power supply and two resistors R and S as shown in this figure here. So the resistance of R is 25 kilo ohm and the resistance of S is 220 kilo ohm. Your switch could be in either positions X or Y. For part A, they mentioned that the switch is now in position X so that the capacitor is fully charged. Calculate the energy E stored inside your capacitor. Okay, so in your case here, your switches are either in position X or either in position Y. So let's just consider your capacitor at position X first. So let me just go and write this out. So if your capacitor is at position X, it should be this loop here. Okay, so you should be getting something that looks like this. Okay, and then when you're talking about a position Y, you're talking about this loop here. What you have is something that looks like this now. Okay, so you should be able to immediately recognize that the left diagram is actually for your capacitor charging up, whereas the right diagram is for your capacitor discharging. Okay, so now your switch is at position X, your capacitor is fully charged. Find out the energy E stored in the capacitor. Oh yeah, I forgot to draw something here earlier. I forgot your power supply. This one here is like this. Okay, so you have a PD of 8 volts here. Okay, and then you have a resistance of 25 kilo ohm. Okay, so now your capacitor is fully charged. Remember just now I told you that when your capacitor becomes fully charged, its PD will be equals to your supply voltage. So one thing to note here is that when capacitor becomes fully charged, it is equal to your supply voltage. Now supply voltage is 8 volts. When my capacitor becomes fully charged, this one must be 8 volts too. And then from there, you may be thinking, there is actually a resistor right over here. Shouldn't the resistor here actually have some amount of PD? Because what you've learned so far in your current electricity or DC circuit chapters in AS was that if let's just say you have something like this, two different resistors, and then this one I told you is 8 volts. This one is R1, and then this one is R2. By right, you should have V1 here, and then you should have V2 here, isn't it? Because what you know is that sum of EMF equals to sum of PD from Kirchhoff's second law. So your EMF E here is actually V1 plus V2. So this one was what you have learned before this, because you notice that there are two components, they should have PDs there. But now in your capacitance circuit here, you again have a capacitor and a resistor. But how come there's actually no PD across your resistor? Now the reason for that is because when capacitor is fully charged, there is no current flow. Okay. From the example that I gave you previously, I mentioned to you that some amount of charge will actually be, let me just redraw it here. when you are trying to charge a capacitor, you tend to have some amount of charge that is being pushed towards one side of your plate. And then this plate will acquire charge of negative Q, and then the same amount of charge of negative Q will be repelled away, causing this plate to become positive Q. When your when your capacitor becomes fully charged, there's no longer going to be any pushing or pulling of your charges. There's no current flow. Okay, so that's why here I can say that when your capacitor is fully charged, there's no current flow. And because there's no current flow, your resistor actually does not have PD. Okay, when capacitor is fully charged, there's no current flow, therefore the resistor does not have PD. Okay, so here you do not assume that your resistor here has some sort of PD. There's no PD actually because no current is flowing. There's no longer any current flow when a capacitor becomes fully charged. So here it will be correct to just say that the PD across your capacitor is actually just going to be the same as your voltage supply. You're still following Kirchhoff's second law here. Okay, you did not break any laws here. You're still following. Okay, so from there, you know that the PD across your capacitor is going to be 8 volts. You now want to find the energy E. Energy E is either half QV, half CV square, or half Q square over C. You can actually make use of what you have found in the graph. You see, they give you a graph initially. So you look at the graph. This is the graph of the PD across your capacitor with charge stored on one plate of your capacitor. So now you already know that your PD across your capacitor is 8 volts. You just try to read here. Your voltage is 8 volts. What is the amount of charge that you should have? Your charge should rightly just be 1.2 times 10 power minus 4 coulomb, if I'm not mistaken. Let me just try and see. Yeah, it's 1.2 times 10 power minus 4 coulomb. So now you have information for voltage as well as charge. Based on the equations that you have here, you would probably want to use the first equation here because you have both charge as well as voltage. Okay, you will use the first one, you won't use the second one because you do not know the capacitance. So here, this one will be E equals to, maybe I should write the workings here for you. This one here is, let me go down a little because I still need to do some workings there. Okay, this one probably what I'll do is I'll write something like this. When V equals to 8.0 volt, Q equals to 1.2 times 10 power minus 4 coulomb. Your energy is actually 1 over 2 QV. You sub that in, you get 1.2 times 10 power minus 4 times with 8. Your energy here would actually be, let me calculate it out. 1.2 times 10 power minus 4 times with 8 times 0.5. You will be getting the answer as 4.8 times 10 power minus 4 joules. This is your energy stored by your capacitor. So let me check the answer. Yeah, it's correct. Okay, so this is all right. Now the part that relates to the discharge of capacitor is actually in part B. The switch is now moved to position Y, so it's actually talking about this one right now. Show that your time constant of your discharge circuit is 3.3 seconds. So you take 3.3 seconds for the charge across your capacitor or stored by your capacitor on one plate to decrease by a third. That one you take 3.3 seconds. Okay, so your resistance here is 220 kilo ohm. This is marked as S in your circuit. So right now, you need to find out what is your capacitance in the first place. Because if you recall time constant is the product of your resistance and your capacitance. You know the resistance already. You just do not know your capacitance. Maybe I should just get rid of this as this one is just in the way. Okay, you need to find out what is your capacitance now before you can actually use your time constant equation. So here, C is equals to Q over B. You just use the definition of capacitance. So this one would just be 1.2 times 10 power minus 4 divided by your voltage. This one, the voltage across it should still be 8 volts because this is the point where you switch to switch Y. Your capacitor was fully charged at that time when you just first switch to position Y. So it's 8 volts, okay? So this one is going to be 8. Your capacitance now would be 1.2 times 10 power minus 4 divided by 8. You will get 1.5 times 10 power minus 5 farads. Then now you can use your time constant equation. Tau is RC. R is 220 times 10 power 3 times your capacitance of 1.5 times 10 power minus 5. You will get the time constant value as 3.3 seconds. So this is shown. Okay, so this is pretty straightforward. Okay, the next part is when you need to do some further calculation. In the next part, they mentioned to you that the fully charged capacitor in A stores a charge of E. Find out the time taken for the stored energy to decrease to 1/9 of its original value from E to E over 9. Okay, so how are you going to do this? This one, let me just clear off all the things here. So they want you to find the time taken for stored energy to decrease to 1/9 of its original value. Okay, and you notice that this one carries a very large amount of marks. It's actually 4 marks. Now, just now, when you're talking about your discharge equations, let's just rewrite your discharge equations here. For your discharge equations, for your capacitor just now, number one, you had Q equals to Q naught exponential negative T over RC. Number two, you have V equals to V naught exponential negative T over RC. And the last one is I equals to I naught exponential negative T over RC. Okay. Now, because this one is talking about time taken for your energy to decrease from this to this, could I also say E is equals to E naught exponential negative T over RC? This one you cannot say so. You cannot just simply assume that your energy follows an exponential decay curve also. This one is not true. Your energy isn't decreasing like that. It's only true for your charge, your PD, as well as your current. Now here I can say this because how are all of this related in the first place? Why do I say that they are actually acceptable to say that they can follow this form of equation? The reason is because if you're talking about I equals to Q over T, T is constant, I is proportional to Q. And then if you're talking about V equals to IR, R being constant, that would mean that V is proportional to I. So like in my case here, since V is proportional to I can say this one is true. And then, sorry, this one is supposed to be the second one. Because I can see that V is proportional to I can say that this relation is true. And then the next one, I can see that I is proportional to Q, so I can also say that this relation should be true. Okay, because they are directly proportional to each other. If I already know that this one is true, if the other quantities are proportional to your current, it follows that this must be true and this must be true also. Okay, but for energy, this one, no, you cannot prove that out. Okay, so you cannot say this. So how are you going to find out the time taken here if you cannot use this particular form of equation? This one, you have to relate the energy with voltage. All right, you have to relate your energy with voltage. Let me just redraw your capacitor circuit here. Let me just see where was it. This one was your original diagram at position Y. This one, I already know that the capacitance value is some value. I can't remember what was it that I calculate out. Let me just try and see what was the value. Oh, wait, I deleted it just now. Q over B, this one should be 4.5 times. This one should be 1.2 times 10 power minus 4 divided by 8. Wait, 1.4. Sorry, 1.2 times 10 power minus 4 divided by 8. If I'm not mistaken, the capacitance value that I found just now was 1.5 times 10 power minus 5 farad. Okay. Because I calculated this very quickly, just let me know if I calculated it wrongly. Okay, so that was your capacitance value. And then your resistance is actually 220 kilo ohm here. Okay, so what the question mentioned is that your energy stored by your capacitor has actually decreased to E over 9. Okay, right now, if I say that my energy has decreased to E over 9, what can I say about my voltage? Let's just assume that your voltage was starting off from V naught. This one I know that the voltage originally was 8 volts. That is true. It's 8 volts. Let's just call this my V naught lah. Okay. So my voltage started off with V naught at 8 volts. If my energy decreased from E to E over 9, how will my voltage change? From V naught to what value? So you want to find this right now. Because you see, both of these are occurring in time t. They are both occurring in the same time t. In the same time t. If you are able to work out how is the voltage changing when this energy is changing, you can actually make use of this equation right over here to find out the time t. So that is what you want to do here right now. You are relating the energy change with your voltage change. So if you want to relate your energy change with your voltage change, there were a few equations that you have learned. E is equals to QV. Sorry, E is equals to half QV. E is equals to half CV square. And E is equals to half Q square over C. Okay, this one is half Q square over C. So I want to relate it with voltage. That would mean that third equation is gone, no relation with voltage, but I can have either equation 1 or equation 2. So the thing here is which one would I want to pick? You will actually pick the second equation here. Because what you do know is that this capacitance value is fixed. Regardless of whatever changes occurs in your circuit, because you're still using the same capacitor, the capacitance value would be fixed. It's constant here. You won't use the first equation here because your voltage can change and so would your charge storm. They are both changing. They are two changing variables, so you do not want to use this. You want to specifically use the second one because there's only one changing variable and the others are fixed. Okay, so now you use E equals to half CV square. So C is constant. That will mean that E is proportional to V square. So right now, this would mean something like this. E2 to E1 will be equals to V2 square to V1 square. Okay, so my E2 is actually E over 9. This one I'll write it here. This one is E over 9 divided by E itself. My V2 square is what I want to find. My V1 square is actually just my V0. Okay, maybe I better just write it here. E over 9 divided by E equals to V2 square over V0 square. Okay, so from here, you ought to be able to work out some sort of relation. Your V2 square is actually 1 over 9 of V0 square, which in turn tells you that V2 is actually V0 over 3. Okay, so now you know that when your energy was decreasing from E to E over 9, your voltage is actually decreasing from V0 to V0 over 3. Okay, so this one you already know the voltage changing, how it changes. So from there, you can actually use this equation straight to find out what is your time t. Okay, so you have to use another equation here. I'm just going to write it at the bottom because I ran out of space at the top. So if I use V equals to V0 exponential negative t over RC, your V0 remains the same as before, but your V is actually V0 over 3. Okay, this is now V0 exponential negative t. Your time constant is 3.3. You already found it in the previous part of your question. Okay, so once you have this, you try to solve, you're going to get something like this. You're going to get ln 1 over 3 equals to negative t over 3.3. So that now your t would be 1 divided by 3, ln that answer times with negative 3.3. You will get the t as 3.63 seconds. Okay, so that is your answer here, if I'm not mistaken. Yes, 3.6 rounded up to 2SF is 3.63 seconds. Okay, let me just get rid of this thing. Okay, this is the answer. So the answer is correct. Okay, so then let me just go back to the last part of your question. Okay, so the last part of your question here, you have a second identical capacitor that's connected in parallel with your first capacitor. State and explain the change, if any, on the time constant of your discharge circuit. Okay, so now, if you notice that they say you are using an identical capacitor, the keyword here is identical, that would have told you that you actually have same capacitance. Okay, you're using another capacitor or same capacitance. So what is actually happening here is that they connect that same capacitor in parallel with the first one. What happens to your time constant? So if you imagine that right now, you have another capacitor, also a capacitance C connected in parallel here. This one is already connected in parallel. Your capacitance in parallel here, you will have to treat it like you would resistors in series, so you can just add them out directly. So this one becomes 2C. So your capacitance has actually increased by 2 times here. So if you refer to your time constant is product RC. Your resistor here is fixed, is constant. So R is constant. That would mean that time constant is proportional to capacitance. So your capacitance, total capacitance is doubled. Let me just write it as total capacitance is doubled. Here, your total capacitance is doubled plus time constant is doubled. because here C increased 2 times, time constant must increase by 2 times 2. Okay, all right. So this one is for this particular part. This one was for the March paper. Your capacitance question actually took out a whole full 10 marks here. All right, so this one is okay. Hopefully, then I'll just clear off everything here and move on to the next question that is related to discharge of capacitors again. So let me clear off the diagram. Okay, have a look at page 7. Next page you will look at is actually page 7 of the separate worksheet that I sent to you last week. Okay, so for the first part, define capacitance of a parallel plate capacitor. This one is just simply charge stored on either plate of the capacitor, per unit PD applied across the capacitor. Okay, so this one is just the definition from your notes that you can recopy. Now in B, you have two capacitors of capacitances C1, C2 connected in parallel to a power supply of EMF E as shown. Show that the combined capacitance CT of the two capacitors is given by CT equals to C1 plus C2. Explain your reasoning. You may draw on the figure 5.1 if you wish. This is actually deriving the capacitances in parallel. So this one here, what you could probably kind of do here is probably you imagine that you have a charge of Q that is QT lah, okay, total charge that's coming out from your cell. It reaches this junction here, it will now split up to Q1 and Q2. So this is the same charge that will be repelled off the other plates too. When you're talking about the charge that is stored on one plate of your capacitor itself, is really just Q1 and Q2 here, okay? Because this one here, you will actually get, yeah, let's not make things more complicated. Just remember that the charge stored on this capacitor is just Q1 and Q2. And then say your PD across each of your capacitors, this one will be V1, and then this one will be V2. Okay, so now you're good to go. So now you apply your Kirchhoff's first law here. QT is not really Kirchhoff's first law, okay? It's more like conservation of charge. QT is equals to Q1 plus Q2. And then capacitance is Q over V such that Q is C over V. So now this one will become CT over VT equals to C1. Hey, wait, did I do this wrongly? Yeah, sorry, I did this wrongly. Q is CV. Sorry, that's why it looks weird just now. This one will be CT VT equals to C1 B1. This one will be C1 B1 plus C2 B2. And then after that, you can actually say that Vt is equals to V1 is equals to V2 is equals to E itself, because you can apply Kirchhoff's second law for this loop. This one will tell you your PD here is actually E. You apply Kirchhoff's second law for this loop. This will also tell you that your PD here, V2 is also E. Okay, so therefore, you have CTVT equals to, maybe I just write that as E. Equals to E, C1 E plus C2 E. This one will cancel each other off. This cancels each other off. So that you now get CT equals to C1 plus C2. So this one is shown. Okay. So this one, if anything, I should write this one is actually related to your Kirchhoff's first law. This one is related to your Kirchhoff's second law. Okay. The derivation of your capacitances always tend to relate to these two laws that you've learned in your AS. Okay. So this one is pretty straightforward. Now, next part again relates to your capacitance discharge. So let me clear this thing off. So in part C, you have two capacitors or capacitances, 22 microfarads and 47 microfarads, and a resistor or resistance 2.7 mega ohms that are connected inside a circuit here. Your battery has an EMF of 12 volts. Show that the combined capacitance of the two capacitors is actually 15 microfarads. So you have the two capacitors here connected in series. So for capacitors in series, you have to treat it like you would resistances in parallel. So this one is 1 over 22 plus 1 over 47 power negative 1. Your total capacitance is going to be 15 microfarads. But let me check first for you. Is it correct? Yeah, it's 15 microfarads. Okay, so your combined capacitance here is 15 microfarads, just like that. Okay. Now, then after that, they mentioned to you this. Your two-way switch is initially at position X, so that the capacitors are fully charged. Use the information in C1, which is the one that you've just done above, to find the total energy stored inside the two capacitors. Okay, so let's consider this now. Your switch is at position X, meaning to say here, the circuit that you need to consider is this black colored loop here. Okay, so it helps to draw it out whenever you do your capacitance questions. So at position X, you are getting something that looks like this. Where this one is 12 volts, this one is 22 microfarads, this is 47 microfarads. Okay, so now you want to find out the total energy stored by the two capacitors. It will probably be better if you try to simplify it as simple as possible for the existing circuit. So this one, you know, you can simplify it even further, where you are supposed to get something that looks like this now. Okay, this one again is still going to be 12 volts, but this one, your combined capacitance, you already found it out as 15 microfarads. Okay, so whatever energy that is stored in this capacitor would be the energy that is stored in these two capacitors. So you would want to work with this diagram. Okay, so now you know the voltage also across this diagram, because here you see you have only one single capacitor of 15 microfarads. If this one is to become fully charged, because your PD is 12 volts here, this one must also be 12 volts. Okay, so you know the capacitance, you know the voltage. So when you're looking at your energy equation, the first thing that will probably come to mind here for you is that you could probably use E equals to half CV squared. You won't use the other two because you do not know the charge. The charge here is unknown, so you don't want to use any of the two equations with charge inside. So this one is half 15 times 10 power minus 6 times with your PD of 12, square it. Your E will now be 15 times 10 power minus 6 times 12 squared times 0.5. You're going to get the answer as 1.08 times 10 power minus 3 joules. This is what you are supposed to get. Yeah, if you round it out to 2 SF, it's going to be 1.1. Okay, so this one is called okay. Okay, then we move on to the next one. Now this one is your discharge again. So let me clear this thing off. Okay, now For the last question here, they mentioned that the two-way switch is now moved to position Y. Determine the time taken for the potential difference across the 22 microfarad capacitor to become 6 volts. Okay, find out the time taken for the potential difference V across the 22 microfarad capacitor to become 6 volts. So if you recall the diagram right now, they tell you that they are in position Y, meaning to say you are now here. You are considering this particular loop right over here. So you try to draw it out, you will see it's actually a discharge circuit. So this one is a position Y. This is what you're having. Something that looks like this right now. This one is 2.7 mega ohm. And then this one is 22 microfarad and 47 microfarad. Okay. So what they want now is for you to find out the time taken for the PD across your 22 microfarad capacitor to become 6 volts. So they're asking you to look at this one right now. They're not asking you to look at the whole arrangement. They're only asking you to look at one particular capacitor inside your circuit. So they want you to find out how much time will it take to become 6 volts. Okay, so that's what they want you to find out right now. So this one, since it's talking about discharging of a capacitor and it is talking about voltage, the first thing that will come to mind is this one. V equals to V naught exponential negative T over RC. Okay, so this is the thing that will come to your mind here right now. So now, if you look at this part here, I told you that they want you to find out the time taken for your voltage to become 6 volts. What is the initial voltage in the first place then? If you wanted to use your V equals to V naught exponential T over RC here, you need to know your initial voltage and your final voltage, and not to mention your time constant. But time constant here, you can easily find it out because you have the value of your resistance and your capacitance here. So you are actually left with trying to find out the voltage here in the first place. You know what is your final voltage? It's going to be 6 volts, but this one is unknown. Okay, so how are you going to find out what is your initial voltage for your 22 microfarad capacitor? Now this is when you have to refer back to the diagram that you've drawn here. Okay, so now think about it. If you look at the second diagram that you have drawn here, this part here, you could imagine that there's a certain amount of charge that's being pushed out from your cell towards one plate of your capacitor. That same charge will be the same charge that's repelled away, so that effectively whatever charge that is stored on your capacitor here, one plate of your capacitor here is really just Q. Okay, so this one here, let me just try and use a separate color. The charge that is effectively stored on one plate of your capacitor here is really just Q. So now you backtrack a little. Because this circuit is connected in series, whatever charge Q that you have here is also the same charge Q that will be stored on either of the capacitors here. Because here you can imagine that this one is a charge Q moving like this. This one would be how the charges are actually being moved across your circuit. Each plate of your capacitor right now would effectively really just store Q only. So you can find out the Q from the diagram below here is also the Q on the 22 microfarad capacitor. Okay, so this way of doing things is actually quite similar to the examples that we've done last week. If you want to find out the specific PD across one part of your capacitor here, you have to kind of like work through it from a simplified diagram backwards. Okay, so right now you want to find out your V for the 22 microfarad capacitor. You need to first find out the charge stored. So you have to look at this diagram here. So right now, if I try to work it out, this one is C equals to Q over V. This one is for the simplified circuit. For the simplified whole circuit. Okay, so my capacitance is 15 times 10 power minus 6. And then after that, my Q is what I want to find. My PD I already know is 12 volts. So that my Q now is going to be 1.8 times 10 power minus 4 coulombs. This is how I find my charge. And that charge will be the same charge that is stored here. So here, I again will use C equals to Q over V, but for the 22 microfarad capacitor. So then this one now would be 22 times 10 power minus 6 equals to 1.8 times 10 power minus 4 divided by V. This V here will now be 1.8 times 10 power minus 4 divided by 22 divided by 10 power minus 6. You will get the answer as 8.2 volts. Or maybe if I use 3SF, this one would just be 8.18 volts. Okay, so now you've already found out what is your V0. Okay, here you already found it out as 8.18 volts. So that 8.18 volts will be this voltage here. Okay, so it started with 8.18 volts. It will now become 6 volts. You want to find out the time taken. So now this one I already know. This one will be 8.18 volts. Okay, so there will be a next step here where you use your discharge equation. V equals to V0 exponential negative T over RC. This one will be 8. This one will be 6. This one will be 6. This one will be 8.18. And then this one is exponential. Okay, this one I have to draw a bit bigger because of the workings here. V equals to V0 exponential negative T over RC. This one is 6. This one is 8.18 exponential negative T over RC. Okay, your RC here is 2.7 times 10 power 6. And this is where some mistakes tend to happen. Which value of capacitance are you going to use? There, a lot of time people say that because you're talking about your 22 microfarad capacitors and you're using this discharge equation here, your capacitance here should refer to the 22 microfarad capacitance. This one is actually not correct. If you have tried to proceed with your working and you wrote this as 22 times 10 power minus 6, this one would actually be wrong. Okay, when you're talking about your discharge constant, your tau equals to RC, this one is actually for the discharging circuit. Your discharging circuit is actually this entire thing. Okay, so this one here, when you're talking about your C, it should be for the total capacitance of your circuit. Because when you're talking about tau equals to RC, is actually applied for your discharging circuit as a whole, not for a single capacitor itself. So right now, your C here, you cannot use the 22 microfarad capacitance. you must use the total capacitance of your circuit, which in your case is actually this one here, 15 microfarad. This is what you found. You see, just now they asked you to find the total combined capacitance, and you show that it's 15 microfarad. That is what you're going to use here. So you don't use 22, you use 15 microfarad. So this one should have been 15 times 10 power minus 6. So that now if you want to simplify your entire working, you should get something like this. This one will be ln 6 over 8.18, then negative t over 2.7 times 10 power 6 times with 15 times 10 power minus 6. So eventually your t should be 13 seconds. Or maybe I just calculate it off first using the calculator because I'm using some pretty exact values here. So ln of that answer times with negative 2.7 times 10 power 6 times 15 times 10 power minus 6. Yeah, I'm getting 12.6 seconds actually. If using my values, I'm actually getting 12.6 seconds. But if you run it up to 2SF, it's actually 13 seconds. It's actually following what your answer is giving. It's 13 seconds. Okay? Okay, now you can have a look at page 30. Page 30 ought to be this one. There's one particularly weird question from here that we can do. This one is November 17 P41. Okay. So if you look at that question now, let me just clear this thing off. Okay, so again, you have two capacitors, P and Q, each of capacitance C. They are connected in series with a battery of EMF 9 volts as shown. A switch S is used to connect to a third capacitor T, also a capacitance C or resistor R in parallel with capacitor P. So switch S is now in position X. Calculate out the combined capacitance in terms of C for the three capacitors. So when your switch S is in position X, you are really over here, so that when you consider your circuit, it should be this whole part that has been highlighted in orange here. Okay, so again, it will be good to try and draw out the circuit again separately. If this is at position X, what you expect to see is something like this now. Like this. Sorry, I need to redraw this. It's something like this and something like this. Okay, so this is what you expect to see right now, where this one was 9 volts. This one is capacitance C, capacitance C, capacitance C. So now you want to find out the combined capacitance of the three capacitors that is listed here. You again try to simplify one by one. You can see that this one is actually in series. Sorry, this one is in parallel. So here I can actually already say that the capacitance in parallel here is treated like I would resistors in series. So this one is C plus C, giving me 2C. So this one, I redraw it. I will get something like this now. Okay, so this one I can't draw the lines properly. Okay, so this is now C and 2C. And this one, again, I want to simplify again, because this one is considered as connected in series now. What I can do from here is that I treat it like I would resistors in parallel. So here, this one, I can say C is 1 over C plus 1 over 2C power negative 1. Eventually, I'll get 2 over 3C. Okay, so let me just redraw this. The simplest I can simplify it then is basically going to be this one. Okay, so this one is still 9 volts. This one is still 9 volts. Okay, so this is really simplified to the max. Now, here you are trying to find out the combined capacitance in terms of, say, the 3 capacitors. This one, you can actually just say that is basically based on this working. Okay, 1 over CT is equals to 1 over C plus 1 over 2C. Eventually, your CT will be 2 over 3C. Okay, you will notice that I actually had to simplify the parallel connection first. Then after that, I can add up the capacitances to find the total capacitance. Okay, so that's how you would do this. And then now, if you look at the next part of your question, find out the potential difference across capacitor Q and explain your working. Okay, this one, capacitor Q is actually this one. Okay, they want you to find out the PD across capacitor Q, and you're supposed to explain your working. So capacitor Q here, I'll just mark it out for you on the diagram that I just drew. Capacitor Q is this one. This is capacitor Q. Sorry, I need to draw it. The way they label your capacitor here is a bit confusing because Q here can mean charge also based on what we've been doing so far. So this is capacitor Q. Okay. Right, this is your capacitor Q also. Okay, so they want you to find out the PD across your capacitor Q, meaning to say they want this PD now. What is the PD across here? All right, so in your case, how are you going to find the PD across here? You actually have to make use of one particular relation. This one you can only see after you have simplified your circuit to the max. So if you look back at your original circuit, the one that is simplified all the way to the maximum, for this part here, when your capacitors are being charged, you will have an amount of charge that is being moved from this end to this end, and it will be the same amount of charge that's being repelled away, such that the charge stored on one plate of your capacitor is really just Q. So now you work backwards, you can actually also say the same thing. That same amount of charge that is being pushed from one terminal of your battery across your whole circuit, because these are capacitors connected in series, whatever charge is stored on one plate of your capacitor is really just going to be Q only. Okay, so this one here, let me find a suitable color. Probably I should just use white, maybe. Can I use white? Okay, white is better. Okay, so your charge stored on each of your capacitors here is actually just Q. Okay, so right now, what you want to do is this. You want to find the PD. You can make use of the equation C equals to Q over V. You make a comparison between this capacitor and this capacitor. All right, you make a comparison between those two right now. So if you make a comparison between those two, before you make that comparison, do you even know what is the PD across here? Because this is the only capacitor connected inside your circuit, you could actually say that this one is going to be 9 volts. This one will have a capacitance, this one will have a PD across it of 9 volts. Okay, this one you want to have this one is a PD of 9 volts across this simplified circuit here. Now you want to find out what is the PD across the capacitor Q here. Okay, so what you can probably say here is that there's something common between those two right now, in the sense that they're storing the same charge. Okay, so right now I can say something like this: Q is constant for both capacitors, such that C is inversely proportional to V. So that right now I can say that C2 to C1 is 1 over V2 to 1 over V1, giving me C2 to C1, V1 to V2, right? So which one is my C2, which one is my C1? Let's just say that this one is my C1, and then this one is my C2. Okay, so my C2 is just C, my C1 is 2 over 3C, my V1 is 9, my V2 is what I want to find. This is my V2. This one was my V1. Okay, so now my V2 would actually be 2 over 3 times 9, giving me 6 volts. Okay, so the answer is 6 volts. So how will you explain it? The part where you're supposed to explain your working, this one is actually based on this, where you say that your charge stored in your capacitor Q itself is the same as that stored by your combined capacitance. So you use the capacitance equation C equals to Q over V. Q is constant, C is inversely proportional to V, thereby giving you this relation. So based on what I've just done right over here, that is the working that you're seeing right over here. Okay. I actually use a different symbols. Instead of saying that is V1, V2, C2, C1, I put it as VQ, VT, I put it as VQ, VT, and CQ, CT, I think. Yeah, you could do it that way also if you wanted to, whichever works for you lah. For my case, sometimes I use numbers, sometimes I use alphabets, right? But the working is the same. So eventually you will get the answer as 6 volts. Okay, that is for this particular question, right? So you'll notice that from all the questions that we've been doing so far, a lot of times you always need to do something like this when it comes to your capacitance question. You have to draw your circuit from the beginning and then try to simplify as far as possible. You need to simplify to the max. And then from there, when you are doing all your calculations, the logic is coming from those diagrams you're drawing. Okay. So this one is okay. Then I move on to the next one. This one is something like state and explain question. All right. So now in B, they now mention to you that switch S is now moved to position Y. State what happens to the potential difference across capacitor P and across capacitor Q. Okay, so this one I'll have to erase off the things that you have here. This one is really going to the part where your capacitor is discharging. So again, it works better if you try to draw your circuit again, just to see what's happening. So at switch position Y, you are now right over here. Okay, so that your entire circuit can be considered as something like this right now. Okay, so this one is at position Y. Now, if you withdraw your circuit, this one will be what you have. This one is your fixed resistor. Then you get something like this. Okay, so this one originally you know is 9 volts. And if you recall what you've done earlier just now, you already found out what is your VQ. Your VQ is actually 6 volts. So this one is your capacitor Q, not charge. Okay, this one is capacitor Q. And then this one is your capacitor P. And then this is your resistor R here. All right. So you already found out that the PD across your capacitor Q is 6 volts. If you apply Kirchhoff's second law for this loop, you should rightly be able to determine that capacitor P is going to have a PD of 3 volts. Okay, so this one here, you should be able to determine that it's going to be 3 volts. Okay, so this is what's actually the circuit right now. Okay, this is how the circuit looks like right now. So here, the question is asking you, state what happens to the PD across P and Q right now, once you have moved to switch position Y. For capacitor P, your PD will actually decrease from 3 volts to 0. So this part here, they tell you it will decrease from 3 volts to 0 volts. Whereas for capacitor Q, the PD will actually increase from 6 volts to 9 volts. This one will actually increase from 6 volts to 9 volts. Okay, so now why does it become like that in the first place? Now you see, in your circuit here, you actually have a resistor. So here, what you could say is that charge or current is supposed to discharge through here. Okay, so right now, what you can think of is that when you first connect your switch to position Y, your capacitors were already having this PD value. They will actually start to discharge through your resistor here. So when they start to discharge through your resistor here, your current flow looks something like this. There will be one current going through like this. This is current from Q. And then there'll also be current going from capacitor P, so that you get something like this. Let me find a suitable color that I can use. Okay, I'll use pink. This one will also start to have current coming out. This one is current from P. Okay, so both capacitors are actually discharging right now at the start. Let's just say at T equals to 0. So your capacitors, both capacitors are discharging. What I can say is that both capacitors discharge, both capacitors discharge through the resistor R. Okay, so now when your capacitor starts discharging, at the same time, your capacitors are also still connected to your power supply. So because your power supply is still connected, because power supply is still connected, when your capacitor Q discharge, let's just say Q first. When capacitor Q discharges, it gets charged back by the power supply. That will explain to you why, therefore, the PD increases from 6 volts to 9 volts. Okay, even though it's discharging, but somehow the PD increases back because you're still, at the same time you're discharging, your power supply is charging you back. So your PD actually doesn't drop. You're actually being charged back. So this one is 6 volts to 9 volt. But what about capacitor P here? Okay, because I say to you that capacitor Q is being charged back as it's discharging, how about capacitor P here? Now, capacitor P here cannot be charged back because of this reason. Capacitor P cannot be charged back because there is already current or charge flowing out of it, opposite to current from power supply, opposite to current or charge from power supply. Opposite to current or charge from power supply. Okay, what I mean by that is you imagine this now. If you have some amount of charge or current that is coming from your power supply, like this is the charge or current from your power supply. It cannot just keep on moving to P, because you see P in the first place was actually discharging current out in this direction, opposite to that of your power supply. You look at this part here, they are actually opposite direction. Your charge or current from power supply wants to go down, but the existing charge or current from your capacitor P is trying to go up. So right now, it can only move one way. So here, because your capacitor P is actually discharging current or charge out in this direction, opposite to the current or charge from your power supply, it actually cannot be charged back. So it will just continue discharging, right? So here you cannot say capacitor B will be charged back. It cannot be charged back. So what happens then is that your capacitor P continuously discharges this one. Therefore, capacitor P continuously discharges. The PD drops from 3 volts to 0 volts. That's how you got to this conclusion here for capacitor P. Okay, right? So it takes quite a bit of thinking for this circuit, but luckily for this particular question, they didn't really want you to explain why it changed the way it did. They just want you to state simply what happens. They didn't want you to explain. But if you want to explain why it's like that, usually is along this line of reasoning. Okay, you can see that it's actually pretty long-winded. Okay, so this is one of the more complicated and harder questions in capacitance so far that I've seen. Okay, right, so this one is okay.